Monitoring outcomes of restoration projects is an essential aspect of adaptive management and can help to demonstrate project efficacy and garner support for future work. But limited monitoring resources can make it difficult to collect robust pre- and post-restoration data. Climate Engine can help you to fill in these gaps by making it easy to analyze cutting-edge vegetation and climate datasets. In this video, we'll demonstrate how you can get started evaluating outcomes of riparian restoration in Climate Engine. In this video, we're going to walk through a demonstration of how to assess riparian vegetation productivity during the pre- and post-restoration period using satellite data while also accounting for climate. The satellite dataset is Landsat. Landsat is a multispectral satellite system that has collected data continuously during its modern period from 1984 to present day. It collects data at a 30-meter resolution, meaning that each pixel in its images is about the size of the infield of a baseball diamond. It is the longest running Earth observation satellite, and so is incredibly useful for rangeland monitoring. Now, I used a term that might be new to you, referring to Landsat as multispectral. Landsat essentially collects measurements of the energy reflected or emitted from the Earth's surface. They are kind of super-powered images that collect measurements of the energy that we can't see, in addition to what we can see. Remember back to high school physics and learning about the electromagnetic spectrum? Well, as humans, we can only see visible light, but Landsat can measure other portions of the electromagnetic spectrum too, like infrared energy. Well, it turns out that the ratio between near-infrared energy and red energy, reflected by plants, can tell us a lot about how productive those plants are, or how actively they are photosynthesizing. Plants that are healthy absorb red energy and reflect near-infrared energy. We can use a value called the Normalized Difference Vegetation Index, or NDVI, to assess vegetation health. With NDVI, plants that absorb red energy and reflect near-infrared energy have high NDVI, whereas stressed plants that absorb near-infrared and reflect red have low NDVI. We can create maps of NDVI to assess where vegetation is most productive. The second dataset we'll use is GridMet, which is a daily dataset created from climate observations that is available for the continental US. We often use GridMet to evaluate drought, and here we'll use it to help to account for precipitation each year. Alright, let's get started looking at data in Climate Engine. In this video, we'll be using the Climate Engine Research app to perform our analysis. Be sure and check out the tutorial videos for demonstrations of how the app works. Both the mapping and charting characteristics of Climate Engine will be important aspects of this video, and we'll start with an example of how we can use maps of NDVI to assess riparian vegetation condition. For our demonstration, we're going to evaluate Susie Creek, a stream in northern Nevada that has received significant management and restoration attention in recent decades by numerous agencies, landowners, and organizations. We'll start by creating a map of NDVI vegetation health during the summer of 2022, which is essentially the current condition. To do so, we'll select Remote Sensing from the Type dropdown, Landsat 5, 7, 8, and 9 from the Dataset dropdown, and NDVI from the Variable dropdown. We're going to take the mean value over our time period and set our time period as last June, July, and August. Click the big green button and we'll get our map. Once we have our map, we can adjust the map's color ramp if we want to make the riparian area more clear. The riparian area immediately pops out as a green ribbon surrounded by the high desert vegetation. This map essentially shows the current condition of vegetation health during the summer months. And we can also evaluate the trends in vegetation health by creating a trend map of NDVI in Climate Engine. To create our trend map, all we have to do is select the Slope of Trend option from the Calculation dropdown. And then we can select the year range that we're interested in. In this case, I'm going to select 1991 to 2020, click the big green button, and get our map. The map shows a strongly positive trend in vegetation productivity in many parts of the stream, but also negative trends in some locations. These maps can be helpful for identifying patterns and changes on the landscape. Another feature of the trend map is the ability to mask out areas of the map based on whether the trends are significant or not. Here we'll use a mask to remove all pixels with a p-value greater than 0.05. The resulting map shows highly significant trends in the NDVI summer data. To dive in deeper to this location, we can look at how the vegetation health has changed through time for this particular location. And the best way to do that is by charting summer NDVI through time. To create a chart, we'll click Make Graph to open up the charting pane. Next, we'll define our region. For this part, you might have a shapefile that delineates a restoration area, which you can upload to Climate Engine. I don't have that for Susie Creek, so I'm going to draw an area around the Riparian area using the Google Earth base map. Here, we are going to create a summary time series map. This means that for each year, we will get a single value, rather than every value for the year. So instead of getting every NDVI observation that Landsat made for the entire time period, we're just going to get the mean value for each year. Then we can define the specifications that we want for our chart. Here we will again use the Landsat NDVI, which is pre-populated for us. We'll keep the computation in Landsat's native 30-meter resolution, and we'll select mean as the statistic both over our region and over our date range. We'll again specify the date range as June, July, and August, and we'll run it for the period from 1986 to 2022, removing the first 2 years of Landsat, which can often have some issues. The resulting chart shows a dramatic pattern in NDVI. Beginning in about 2008, we see that vegetation productivity began to increase dramatically as the stream responded to restoration actions. Now, it is important to be able to control for precipitation, because if there was an increase in precipitation during the same time period, that could account for the change in productivity. So here we're going to lean on grid-met precipitation data alongside the Landsat NDVI data to make sure that the vegetation trends are not related to broader climate trends. To add precipitation to our chart, we're essentially just going to update our existing chart and add precipitation data on top of it. To do so, we're going to have to change our chart to a 2-variable analysis. We'll keep variable 1 as the Landsat NDVI data, but we'll update variable 2 to the grid-met precipitation. Select climate and hydrology from the type dropdown, grid-met from the dataset dropdown, and precipitation from the variable dropdown. We'll keep the computation resolution, statistic over mean, and statistic over the date range as the defaults, but we will update the day range. Here, I want to capture the day range as the precipitation during the spring and summer that would be contributing to the vegetation. So I'm going to select March through August. And I'll make the year range match the years I set for NDVI Landsat from 1986 to 2022. The resulting chart shows that precipitation has been highly variable from year to year, but that the increase in vegetation productivity does not appear to be tied to precipitation. To test this further, we can make one final chart in Climate Engine, a 2-variable scatter plot. In the 2-variable scatter plot, we're going to assess the relationship between precipitation and vegetation production directly. To create this plot, first select 2-variable scatter plot from the dropdown. Then we'll run the same variables, but we probably want to switch them so that Landsat NDVI is variable 2. This will put Landsat NDVI on the y-axis, which makes sense since we want it there since NDVI will be responding to precipitation to some extent. Once we have all the settings set correctly, we can go ahead and click Get Time Series to produce our chart. Overall, we see quite a noisy relationship. There doesn't appear to be a strong relationship between vegetation productivity and precipitation at all, which is what we would expect given our previous investigation of the time series. However, the last thing that we want to do here is to evaluate the pre-restoration period separately from the post-restoration period. Select Compare 2 year ranges from the scatterplot options. By 2010, the restoration efforts had started to have a significant impact, so we can use that as the cutoff period and compare the period from 1984 to 2010 to the period from 2011 to 2022. The resulting chart shows a really clear relationship. It shows that accounting for precipitation, vegetation productivity is much higher in the post-restoration period than in the pre-restoration period. We can even add the 95% prediction interval for the pre-restoration period and the trend lines for each period, and see that each year since 2011 has had higher productivity than we would have expected without restoration. Side note that the prediction interval shown on the chart indicates our degree of confidence in where we can expect an individual data point to be located given the data from the pre-restoration period. And we can see that during these periods that precipitation does have a relationship with NDVI. Just that the most important driving variable was the change in management that occurred for this particular location. This is a statistically robust way of evaluating riparian restoration outcomes that was actually published by the Climate Engine team in collaboration with researchers at USGS. Susie Creek is a dramatic example of restoration success, and not every location will have these results. In the examples from the aforementioned publication, 3 of the 4 stretches of stream seemed successful, but 1 did not achieve a meaningful outcome in terms of vegetation productivity. Nonetheless, the approaches shown here are robust ways to test for and evaluate effectiveness of restoration in riparian areas. Thank you very much for joining me. If you found this video helpful, we'd really love to hear from you. We're hoping to make more tutorial videos like this to help to demonstrate how you can start using Climate Engine in resource management and other contexts. So we'd really love to hear from you, hear where you see potential to use the tool, and who knows, maybe we'll be able to respond to what you're asking for. So be sure and subscribe to the channel if you like what we're producing, and come back and see what else we're up to. Thanks again.